Hello everyone. We are in module 3. Under module 3, we are going to learn about general probability concept. So in this module, you need to know about complement rule, addition rule, Venn diagrams, conditional probability, and how to use tree diagram. Then be able to define independent dependent events. So independent and dependent events. And finally, Bayes theorem. So in here, the thrust tree, and actually the fifth one, we did in module 1. So these things you learn in module 1, even though they are repeating here again. Okay. So the lecture actually focus only on conditional probability, independent dependent events, and Bayes theorem. So if you are not sure about the complement rule, addition rule, Venn diagrams, tree diagrams, I advise you to go and watch module 1 video. In there, we cover these things. Okay, so first we go through conditional probability. After that, we will learn about Bayes theorem. In order to learn Bayes theorem, you really need to know about conditional probability. So Bayes theorem depends on conditional probability. So conditional probability, what is it? It's basically a calculating probability by knowing that probability of an event by knowing that another event occurred. So we use a notation. I mean, the notation wise, we use this line to denote that what happened or given. Okay. So this means that B already happened, or we would call this line as given. So given B already occurred, what's the probability of occurring event A? Okay. I mean, for example, let's just say you want to calculate probability. One of your friend, let's say your friend passing, let's say exam P. Okay. Now, yes, you can calculate this probability, but let's say that friend tell you that something else. Studied 3 hours every day for last 3 months. And then you are calculating this probability, the pass exam P. So these are going to be two different values because, of course, having this extra information going to change the probability. So here you can say this is called as conditional probability because it's conditioned on this given event. Okay, so that's what we want to calculate. So this is our conditional probability. Probability A given B. That's how you call it. This is probability of if I write the long way, probability of occurring event A given that event B already occurred. Okay. So we would, in simple way, we would say A given B. Okay. So probability of A given B is formula wise, it's going to be probability A and B divided by probability of B. Okay. So notation wise, A given B, I mean the formula wise, is going to be probability A and B divided by probability of B. Now let's say you change the given event. For example, let's say you change B to be A and A to be B. So then probability of occurring B, given that A occurred, probability B and A divide by this one, okay, so which is probability of A. So you can see the difference, okay. So they are not same. These are not going to be same. Probability A given B is not same as probability of B given A. Even though numerator is same, these look like same, but the denominator, that's different. Okay, so you can see that this is different from this. Okay. Okay, so this is conditional probability formula, and upon this formula, you can really build a Bayes theorem. But before that, we will do some examples and try to understand this concept very well. Let's go next slide. So here you can see a few formulas for the conditional probability. The first one says what? Probability of A given B plus probability of A complement given B is going to be 1. Why is that? You can actually expand this. This is going to be what? Probability of A and B over probability of B. And this is going to be probability of A complement and B over probability of B. So if you draw the, so this is going to be basically probability of A and B plus probability of A complement and B over probability of B. So, I mean, in a way, you can understand this going to be true because let's say you have this Venn diagram. Okay, this is A, B. So first you have A and B, which is going to be this one. Okay, that's this. Then the A complement and B. So what is A complement and B? If you shade area correctly, A complement is outside of A, so which is going to be this. And then the and B, so you have to intersect with B. So at the end, you would get this area. Okay, so you would get basically you would get B. Okay, this area. That is the one which colored by both. Okay, so this entire thing end up as probability of B. So you have probability B divided by probability B, which is going to be 1. So that's the first rule. And then you can you can use addition rule. You know that A union B is probability A plus probability B minus probability A and B. But in this case, you have condition given, so you can use that rule and get this one. So the lastly, you have the probability A given B and C, which this is basic. This is kind of like a look like Bayes theorem, but it is going to be it is something you can prove using conditional probability rule. See whether you can do this. So if you expand this, what is that? As probability A and B and C divided by probability B and C. Now expand the other hand. So if you expand this part, you can see that probability B given A and C. What is that? This is probability of B and A and C over probability A and C. Then you multiply it with probability A given C, which is, let me write here probability A given C, which is basically if I expand probability A and C over probability of C, then you are dividing by this part, that's going to be actually probability B and C over probability C. So you can see that this is to cancel, this is cancelled, and you end up with probability B and A and C over probability B and C. Okay, so you kind of like you can prove it. So these rules are very useful when you are doing problems. So here you see the first problem under conditional probability. This one says insurance company. That's in insurance company, 8% of insured are good drivers. So we have good drivers, 80%. The probability that one policyholder file a claim given that he's a bad driver. So let's say file a claim as event A. And then from here, by the way, from here we can say bad drivers. How many are there? 20%, no? Because total need to be 100%. If 80% is a good driver, then the rest should be bad drivers. So basically, this is good driver complement. Okay. So this is probability of good driver. Let me write that too. Okay. So file a claim. If it's event A, then they are saying that probability of event A given that a bad driver, it is good driver complement, is 0.7. Calculate the probability that no claim payment and the driver is a bad driver. So they are asking what's going to happen if it is no claim. File a claim is A, then no claim, going to be A complement. So we want to calculate A complement given that driver is bad. Good driver complement is bad driver. So this is basically a bad driver. So this one, if I go back to the formula here, you can see that the first one, probability A given B plus probability A complement plus B is 1. So if I use that, this one plus probability A given is going to be 1. Now this value we know as 0.7. So basically probability A complement given a bad driver is going to be 1 minus 0.7, which is 0.3. Okay, that's how you do that kind of problems. So we learn tree diagrams in module 1, but we really, we know how to calculate probability. Usually you go through these branches and you just multiply. If this is 1/2, this is 2/3, and in order to get the probability of this, what you do, you multiply 1/2 times 2/3. Okay. So what is that? What is this? What is the probability in these tree diagrams? They are actually conditional probability, okay, given the prior event along the path had occurred. So if you look at this, let's say this is event 1, and then let's say this is event 2. Then when you are in here, you know that event 1 already occurred. So you are really calculating probability that occurring event, the second event, given that the first event occurred. Okay. So let's say this is A, then this would be probability of A. And this would be actually probability, if this is B, this would be probability of B given A. Okay. So when you multiply these two probabilities, what you get, probability A time probability B given A, which is going to be what? If I expand probability B given A, that's probability B and A over probability A. So when you multiply these two, what you're really getting is these two cancel out, so you get probability B and A. Okay. So the probability of occurring both events, that's what you are really calculating when you multiply. Okay. But these probabilities, those are actually conditional ones. Okay. You may have more than one branch, like if you have 3 events, then this is A, this is probability of A, and this is B, but this is going to be actually probability B given A because A already happened. And this is C, then this probability B, C given A and B both occurred. Okay. So forth. That's how the probabilities are propagate through that. . So here you can see one of another example. You can see that there's 11 balls in the box. So you have box. So there are 11 balls. And they are numbered from 1 to 11. Okay, so you have like 1, 2, so forth, all the way up to 11. You need to draw 3 balls from the box without replacement. So you are taking one by one without replacing it. What's the probability that the number of first ball is even? So if I take if I draw tree diagram, so this is the first ball. And what's the probability of drawing even ball? Since there is 11, and then how many evens? So there are 1, 2, 3, 4, 5. 5 even numbers. So, and then how many odd numbers? How many odd balls? There are 6. Okay. Then the second ball, when you're writing this, you can see that since you already know that you drew, you took one of even ball, you know that there's only 4 left. So it's conditional because you know the information. It is a conditional probability, 4 out of 10. And since you already know that only you took one even ball, you know that the 6 of odd balls still there. Okay. So you can see these are conditional probabilities. The same way here, you can see that if you take one of odd, then you still have all the even. So it's 5 out of 10, and this would be 5 out of 10. Okay, because you already took one odd here, so the remaining odd number of balls are 5. So now we can expand it. This is going to be 3 out of this would be 3 out of 9, and this would be still 6 out of 9. This one would be since you took 6, I mean you took one odd ball, there would be only 4 left. And then since you took only one more, then there's only 5 left. So here you took one even, so only 4 left now, and 5 of odd. And then here you took one odd, so you left it for the 5 even, and 4 odd. So this is even, odd, even, odd, even, odd, even. Odd. So what is the probability that number of first ball is even? So the first ball even is going to be 5 over 11. What's the probability that second ball is odd given that first ball is even? So second ball is odd given that first ball is even. So that's going to be this. So you multiply it 5 over 11 times 6 over 10. What's the probability that the third ball is even? So you have all these scenarios, you have to multiply, and I would leave it as exercise for you. So here you can find one of SOA example. This one says that a blood test indicate the presence of particular disease is 95% of the time when the disease is actually present. The same test indicate the presence of disease 0.5% of time when the disease is not actually present. 1% of population actually has the disease. So calculate the probability that a person actually has the disease given that the test indicate the presence of the disease. So so this one is going to be this one is basically conditional probability. So you can start writing like y is a positive test result. Okay. Then you can write d as disease present. You know, to get positive test result, it doesn't have to be the disease to be present. Okay, for example, when you test for COVID, sometime you may get positive COVID test result even though you don't have COVID. Okay, so it's possibility. So so it is possible to get positive test result without disease. So now here you can see that a particular disease 95% of time when the disease is really actually present. So given the disease present, the test result is positive, indicate the presence. That's going to be 95%. Okay. Then the same test indicate the presence of disease 0.5% of time when the disease is not actually present. So it shows positive, but when the disease is not actually there. So D complement is disease not. Disease present mean actually, okay. So this one is going to be 0.05. Then it says 1% of population actually has the disease. So that's basically probability of disease, actually, 0.01. So we are asking calculate the probability that this person actually has disease, has the disease. So actually got the disease, given that test indicate the presence of disease. So it's the other way. Okay, so given part is test indicate the presence of disease. So basically probability of given positive, disease is there. Now, this is actually a Bayes theorem problem. Okay, I think this should have been there after the Bayes theorem. But anyway, let me give you some idea how to do this. So you can see that this is going to be what? This is going to be probability d and y over probability of y. Okay. So the question becomes how I calculate probability and y. So let's think about this. And I can write this as probability y given d time probability d. You can expand this and you will see that it's going to be same as probability and y. So it's going to be 0.95 time 0.01. Okay. Then the other one, probability of y. Now probability of y, you can calculate using a little bit different approach. You can write this as probability of y given d time probability of d plus probability of y given d complement time probability of d complement. That's coming from actually this second result. Let me go. It's not here. But anyway, you can expand this. For example, if I expand this is what? Probability y and d over probability of d. And what is this? Probability y and d complement over probability of d complement. Probability d time probability d complement, probability complement. And that would end as probability of y and d plus probability of y and d complement, which is going to be probability of y. Okay, so you can prove actually. So you can calculate this probability of y using this formula. This is actually the Bayes theorem, by the way. So this part you can, this is going to be 0.95 and probability of d, which is 0.01. And this part is going to be probability of 0.5. Probability of d complement, what is probability of d complement? It's 0.99. Okay, because using complement rule, you can get that. So this part is going to be 0.9. So you have both, and then you can find the answer for this one. Okay, so answer should be B. So so you can see that you can use conditional probability to solve this kind of problems. So next we have this idea, two events are independent. So what that mean? Of course, two events are independent if one cannot affect the other. That would be the intuitive idea. So we know that conditional probability, A given B. So knowing this event B already occurred, if that's not going to change anything, then that means A and B are independent. So basically we are saying that whether you have knowledge about event B occurred or not going to change um, the probability of event A. Okay. In another way, I can say B given A is same as probability of B. Okay. So this is called as if if A and B satisfy this property, then they are independent. Okay. So if A B satisfy this rule, then A B are independent. Now, if I expand this side, what's going to happen? Is the probability B and A over probability of A. So I can cross multiply and I would get another rule. If you have two events where probability B and A equal probability B times probability A, then they are independent. Okay. So you can use one of these rules. Okay, so you can see that. So this is also called as multiplicative rule. For independent event. Okay. You have a multiplicative rule for dependent event. For example, probability if you have two events which are dependent, then the multiplicative rule is going to be probability A times probability A given B, and the probability B given A. That's the multiplicative rule for dependent events. But if it is independent, then this turn out to be just probability of B. So So here you can find another example. A and B are independent. Now, by the way, independent and mutually exclusive are two different concepts. Okay. So here, what did that mean? Probability A given B is same as probability of A. Mutually exclusive means probability A and B is going to be 0. Or in other words, this side is probability A and B is same as probability A times probability B. This side should be always 0. So just understand that these two are two different concepts. So here you can see that A and B are independent with probability A and B complement is 0.2, probability A complement and B is 0.3, find probability A and B. So how do you get probability A union B? So A and B complement, let's see. A and B complement, that's this one. Okay. A and B complement. And then this one, A complement and B, A complement and B, and that's this one. So you can see that so what's going to be the probability of A? That's going to be if I put here X, it's 0.2 plus X. Probability of B is going to be 0.3 plus X. Okay. Then the probability A and B is going to be, since they are independent, it's going to be probability A times probability B, which is going to be 0.2 plus X times 0.3 plus X. Okay. And then probability A union B is going to be probability A plus probability B minus probability A and B. I think maybe we have to say the okay, I'm not sure. I'll post. I'll check this again, and I'll post the solution into D2L. Okay, so here you can see another few examples. Please try these problems. If you don't know how to do it, just post it in D2L. You can see that here in this slide, I'm mentioning that the independent events and disjoint events, they are two separate types of events. So I want to answer you. I wanted to answer this question: whether mutually exclusive events are independent, whether independent events are mutually exclusive. Okay. So try to answer this. And if you're not sure, you can search it Google, and if you're not sure, then you can post in D2L in the discussion board, so we can make a discussion about that. Okay, so that's all for the conditional events. So next one is Bayes theorem, which is going to be a separate video.